Starbursts. Stars are born when the dust and gas in a nebula condenses together. This continues until it gets hot enough to cause a reaction. This reaction blows away the rest of the dust and gas, forming planets and asteroids around the star. Nebulae. There are two different types of nebulae. The first is emission nebulae. Radiation from the star heats up the nebula, causing the hydrogen gas to ionize. They emit radiation which is often seen as a red light, but there is also invisible radiation given off, like radio waves. And the second is absorption nebula. These appear as dark patches, not light ones. They are dark because the gas and dust block the light of the stars behind. Star deaths. Eventually stars use up all the hydrogen in their cores, and then use up the hydrogen in their outer cores. At this point, it expands and becomes a red giant. Now one of three things happen, depending on the size of the star. Stars up to 4 solar masses. The red giant disperses its outer layers and becomes a white dwarf. The outer layers form a huge planetary nebula, called because the first few observed looked like planetary disks. Stars from 4 to 25 solar masses. The red giant disperses its outer layers and explodes as a supernova, leaving a neutron star. These are so called because they are made of neutrons. They are very dense. They rotate rapidly, emitting radio pulses from their ends, which radio astronomers detect as light and heat. The outer layers form supernova remnants. Stars over 25 solar masses. The red giant disperses its outer layers and explodes as a supernova, leaving a black hole. They form as their mass collapses in on itself. It has a huge gravity, so nothing can escape once it has entered, not even light. Evidence proving their existence is binary stars, which are seen to orbit them. They spin so fast they give off X-rays, which we can detect. They have such large gravity they eject these particles light years away. Spectral lines. Spectral lines are the equivalent of a fingerprint for a star. Elements and compounds have unique spectral lines. Therefore, if we study the light coming from a distant star or galaxy and look for the spectral lines present, we can tell which elements and compounds are present and their quantities. This is a very useful analytical tool. Star classifications. O. Ionized and neutral helium, weakened hydrogen. Bluish and above 31,000 Kelvin. B. Neutral helium, stronger hydrogen. Blue to white, 9,750 to 31,000 kelvins. A. Strong hydrogen and ionized metals. White, 7,100 to 9,750 kelvins. F. Weaker hydrogen and ionized metals. Yellow to white, 5,950 to 7,100 Kelvin. G. Still weaker hydrogen, ionized, and neutral metals. Yellowish, 5,250 to 5,950 kelvins. K. Weak hydrogen and neutral metals. Orange, 38,000 to 5,250 K. M. Little or no hydrogen, neutral metals and molecules. Reddish, 2,200 to 3,800 K. HR diagram. An HR diagram is a graph which shows classification, or surface temperature, against energy emitted, which is luminosity. Shows stars fall into 4 main groups. The position of the stars depend on their mass, and it shows the evolutionary period of a star. Neutron stars or black holes don't appear because they have low luminosity.